Michael, we're going to do some burning of stuff.
Okay.
So I just want to caution you that you shouldn't try this at home because you never know about a fire. It can get out of hand.
Okay.
I have a fire extinguisher standing back in the back there, but we'll be real careful, okay?
Sure.
All right. Now, we're going to burn things that you normally would find around the house. So you got your safety glasses on?
Uh-huh.
Okay. Here's a piece of newspaper. I assume you burned newspaper at some time or other in a fireplace or... So burn it and hold it right over there because the important thing is not the flame itself, but what's left after the flame. Now, see that amount of ash that's left behind?
Uh-huh.
Yeah. What is that? Do you know?
Well, that's the minerals that's been in the paper.
Well, it could be, well, as a matter of fact, it's continuing to burn, and some of the ash is getting very little ash left behind. Actually, when they make paper, newspaper, they try to get rid of as much of that stuff as possible, okay? So the minerals that are in the paper make a difference as to how much ash is left behind. You've burned a magazine, haven't you?
Yeah, I have.
What happens with that?
Well, there's a lot of ash left behind because there's so much...
As a matter of fact, in paper like that, they put clay in order to make a nice smooth surface so it'll take the print well and produce colors well. So there's a lot of ash left behind there. Now, scientists use this technique very often when they're analyzing material. They often burn it to find out what kind of mineral matter might be in it. So that's a lot of ash.
A lot of ash.
Yes. How about paper toweling?
Well, there won't be as much ash to that because there's not that many materials in it.
They're trying to make it nice and thin so it'll absorb liquids. Okay, try that one. Burns up to practically nothing. And flash paper. Do you know about flash paper?
That's the stuff that Lala was using.
What'd she say happened?
Well, she said that it disappeared as soon as it caught on fire.
So here, take it with the prongs and hold it at the very top.
Okay.
Like that, right there. Okay. And just over the top of the candle flame.
Ooh.
She was right, wasn't she?
Uh-huh.
It disappears completely. Well, that's the sort of test that scientists would do when they want to know the mineral content. But then every once in a while, they run across the chemical reaction that produces more ash, material at least, than what they started with. In fact, you and I did that once, didn't we?
I think so, with the volcano.
Yes. What did we do? We put a bunch of chemicals together.
Yeah, and then we put a flame in there, and it just spewed all over the place.
Yeah, well, look at that chemical right there.
What is it?
Well, it's a little pellet that I don't think anybody's found any practical use for it except to make Pharaoh serpents. You remember who Pharaoh was? The Egyptian king? Well, that's what they call them. I'll put a bunch of them down here like this. And you've never played with these on 4th of July?
No.
Well, they're a lot of fun. I'll light them and you watch. Now, notice how much space they take up right now. About, what, half a pea? All right, I'll light them and you watch.
Oh, yuck.
What do you mean, yuck?
Oh, it's all coming out.
Don't they look like snakes?
Oh. Look at that one.
Yeah. You want to pick it up?
So that's the ash?
Yeah, that's the ash. Here's a couple more. Once you get them started, they create all kinds of ash and they come out like a snake. You can see why they're called Pharaoh serpents. As I say, this has no practical use whatsoever except to make a lot of ash. And then one time a scientist was working in a lab doing some experiments, and he sort of accidentally discovered something that would create much more ash than that, and he published it so that you and I can do it. Here's the material we're going to heat up. How much is that?
It's about half a cup.
Well, quarter of a cup, half a cup, something like that. Put it in that can.
Okay.
Now I'll add some acid.
What's the acid for?
Well, there's a complex chemical reaction going to take place, and I don't know what this guy was doing when he mixed all these things together. But anyway, he did, and then he heated it. So that's what we'll do. So now it was sort of a gooey mess down there in the bottom.
Yuck.
What happened to the... Here it is. Okay, so we'll now heat it up and see what happens when a scientist does an experiment in which more material is created than when he started, or at least that's what it looks like. Now, it'll take a while, and I would not suggest that you lean over and look inside the can. Just take my word for it, okay?
Okay.
You hear something happening?
I hear some crunching.
Yeah, some bubbling down at the bottom.
There's a lot of smoke now. I could hear it. It's coming up. Oh, wow. Excellent.
How do you like that?
Holy, that just built up to a lot of...
Yeah, that is what I would call a lot of ash. Remember, we started out with what, about a quarter of a cup or eighth of a cup or so? And look what's left behind. It's kind of interesting stuff, too. Looks something like the Pharaoh serpent, only bigger. This invasion can start from one tiny spore, so small it's invisible. If the conditions of temperature and moisture are right, the invader can spread a network of filaments across its food. It can't make its own food, so it must take its nourishment from energy stored by other plants or animals. The invader can grow thousands of round spore cases that split apart to release millions of spores. Each can continue the process if it lands on the right food and the conditions are right. That's what happens when a slice of bread is invaded by the plant you call a mold. Are you ready?
Yeah.
Okay. You did something strange with your eyes, I think. We'll see. As you know, it takes a while for these pictures to develop.
Yeah.
This is an automatic camera. But the reason I wanted to take your picture, even though I'll give it to you later if you'd like, I wanted you to tell me how long did the flash last?
It was pretty fast. I couldn't really tell.
No, even if you had a stopwatch, you wouldn't be able to time it, would you? It was much too fast. Well, today you and I are going to find out by actually measuring how long the flash lasts with my oscilloscope. You know what an oscilloscope is?
Yep.
What does it mean?
It measures waves.
Measures waves, right. And by setting the dials, you can measure various kinds of waves.
Yeah.
Well, I'm going to set the camera here in this vise, and I put a little close-up lens on the front so that we can take a picture of the screen.
Okay.
Okay? I have to set the reset button here like that. Go ahead and take a picture.
Okay.
Did you see what happened to the screen on the scope?
Yeah.
Because I have a light meter set up here.
Mm-hmm.
When the flash went off, the light hit this part of the light meter here, and you see what happens when I put my fingers over it?
Mm-hmm.
What happens?
The little needle goes down.
Mm-hmm. And when I take my finger away, it goes up.
Yeah, it goes
So
up.
what are we changing the light to? Electricity.
Electricity,
Yes,
yeah.
electricity. Because that's what a light meter does. It changes light energy into electrical energy. Okay, there's a cord that comes down here and connects over to the oscilloscope.
Yeah.
So we can use this to tell set the oscilloscope up so it'll measure the amount of light. But it won't start measuring until the first piece of light hits that little exposure meter. Then it sends a blip down here and away it starts across.
Oh.
Okay. Here, let's take a look at the picture that you took.
Okay.
Each one of those black lines represents 0.5 milliseconds.
Okay.
Okay, so notice that the shutter stayed open for the full length of time. How many? All the way. 6 of those lines?
Yeah, there's 6 of them, so it must be 3 milliseconds.
3 milliseconds. The shutter stayed open.
Yeah.
But now the camera has a built-in light sensor. And as soon as enough light comes into that sensor, it starts turning the flash off. So how long did it leave the flash on? In other words, it started it here and then it turned it off over here. So how long did it stay on about?
It stayed on for 0.25 milliseconds.
Yeah, it's very short.
Mm-hmm.
Now, you know the reason for that is because we are relatively close here.
Yeah.
It's like if I took a picture of you from close by, the light would bounce off your face and come back to the camera and would be quite bright.
Yeah.
So the sensor says, turn off that light. If I took a picture of you from further away now, is the light going to be weaker or stronger when it gets back here?
It's going to be weaker.
So the light would last longer in order to make sure there's enough light. Well, instead of backing this camera off across the room, I'm going to put a piece of tape over the light.
Okay.
That will, in effect, mean as though I backed away, because less light's going to come through. Okay, I'll set the reset button. You fire. Take another picture. Okay, now what happened this time when I put the tape over the front?
The little needle didn't go as high.
Didn't go as high, but did you notice how long it lasted?
It lasted longer.
You think so?
Yeah.
Okay.
I do.
So that means our exposure, when we look at it, that it ought not to be a peak like that. It ought to be longer.
A gentle sloper instead of a mountain.
Gentle sloper?
Yeah.
Okay. Like that?
Yeah.
Okay, now how long would the shutter stay open?
3 milliseconds
Same
again.
time, right?
Yeah.
So now how long did the light last?
Lasted 1.5 milliseconds.
How do you know that?
Because you can see the light getting, or weaker.
Yeah.
Weaker.
Weaker, but it lasted, well, here's the first one.
Yeah.
Which one lasted the longest?
The bottom one.
Yeah, as though you were further away.
Yeah.
So now you've timed it. How long, when somebody asks you how long does the flash last on a camera, what are you going to say?
I'm going to say it lasts.
Thousandth of a second, certainly.
Okay.
Depending entirely upon how far away you are, because if they have an automatic camera like this, how far away you are determines how long it lasts.
Yeah.
And of course, the reason for doing all this is to take a beautiful picture of the model.
Oh, yuck.
Yuck? Oh, I don't think
Gross.
at least the camera worked well.
Look at my eyes.
Yeah, I thought so. Jason, you said you tried to make sugar crystals and you weren't too successful.
I've never had them work.
Okay, well, here are all the ingredients you need, right? So go ahead. What did you do?
Well, I put the water in the glass.
Okay. And then what?
Okay, I took sugar and put quite a bit in at the beginning.
Mm-hmm.
Mix it up.
And you kept adding it until it was what kind of solution was it? Saturated solution?
Yeah, it
What
couldn't
is-
hold anymore.
What does that mean, saturated?
Yeah, it can't hold anymore. It's got as much as it can hold.
Okay. Let's assume that that's a saturated solution. Then
Okay.
what would you do next?
Well, I'd put a little weight on the end of the string so it would hold down and just hang it in the glass like that.
And then nothing happened?
Nope.
What happened?
Well, usually what would happen is you'd just get a crust on top and it would crust around the edges and you couldn't see anything and you'd pull it out and there'd be nothing
okay,
on it.
well, I've had quite a lot of success working with sugar crystals. In fact,
Wow.
you can grow one like that very, very easily. Look at it. Isn't that a beautiful one? You shouldn't
Yeah.
have any trouble. First place, it takes a long time. How long did you wait?
Maybe a couple weeks.
Well, at least that. Now, do you know the theory involved with what makes how a crystal forms inside a solution like that?
Well, sort of, 'cause like it's got all it can hold, right?
Yeah.
So then when the water evaporates, there's not enough room for them all and they start to stick together and
Okay,
stuff.
but the important thing is the rate at which the water evaporates, because the little sugar molecules are dissolved in the water, and you should have it so that at the time when it begins to slow down, it's next to another sugar molecule and can attach onto it. If you evaporate it too fast, they'll deposit wherever they happen to be. So the rate of
okay.
evaporation is important. In fact, one of the things you can do is to cover the glass like this to make it evaporate very slowly. See, I've got a little
I see.
slot in there, and you can pull it down like that, so that it should evaporate as slowly as possible. The more slowly it evaporates, the bigger the crystal we're going to be, because
Okay.
they'll slow down at the right time. Then, the other thing is, did you start with hot water?
Yep.
You can start with hot water if you want, but just make sure that before you set it up, it's cool and no sugar is precipitated. Because if you do that, here's what happens. It'll start collecting on the bottom, and that was one I grew that was on the bottom of the glass.
Why is it that funny color?
Well, that's because I sprayed it with paint so that you
Oh,
can see
okay.
you can see all the little planes.
So it isn't transparent
Right, it
anymore.
isn't
Okay.
transparent anymore. And also, you know, the sugar is dissolved in water, so you could drop water on this and it wouldn't dissolve. But that's what it looks like when you let it just evaporate it fairly quickly and let it all accumulate at the bottom. If you let it go long enough, you can get a great big one like that. Look.
Wow. That looks sort of dull and worn away.
Well, that's because I've been handling it, but you can fix that very easily by putting it back into a solution, and the crystals will reform.
Oh,
So that's an easy way to do it. So now, do you think you can try it again and think you may be able to be successful?
I'll give it a try.
Okay, just make sure that you have a saturated but not super saturated solution, okay? Then hang the string in it and control the rate at which it evaporates. So it ought to be in a fairly dry place with a cover on the top so that you can control it.
Okay.
You should have no trouble at all. And one of the nice things about growing sugar crystals is they're non-poisonous, and you can even eat them.
Yum.
In fact, there is a kind of candy called rock candy. And
I've
all
had that.
Right, and all they are sugar crystals grown just like that. You no doubt have held one of these in your hands many times, but you probably have no idea when. It's not a donut, but much, much smaller. It's the shell of a tiny marine animal. They grow together to form ball-like dwellings for underwater plants. They're studied by scientists, including Dr. Walter Dudley of the University of Hawaii, who took this photograph. When you hold one of these in your hands, you're probably in school, because millions of them together make up a stick of chalk. Darren, here's a sort of magic spool, or you can call it that anyway. What it really is the spool that you get when you buy ribbon to put around a package. You put it here on the table, and you can actually do this on the floor too. I can make it roll forward by pulling on the ribbon.
Oh,
Nothing
neat.
surprising, right?
Oh,
But
not
by
really.
pulling on the same ribbon, I can make it come back.
Come back?
Yeah. By pulling on the one ribbon, I can make it go forward, and by pulling on the same ribbon, I can make it come back.
How'd you do that?
Well, it's all based on a scientific principle that maybe just to sort of shorten it up for you, in effect, what you're doing when you pull, and you pull at a fairly high angle here, you're putting pressure on this part of the spool, and that makes it go that way.
Oh, I see.
Then lower the angle like this, and you're in effect pushing on this side of the spool, which makes it roll that way.
Okay.
So here, try it.
All right. Oops, better straighten that out. Okay.
The high angle, and now the low angle. Yeah, very good.
It's a little too much.
Okay, once more, try it now.
Okay.
You don't have to be quite that high, I don't think.
Okay.
'Cause,
Yeah, doesn't want to go straight.
well, you've got to sort of keep the ribbon near the center of the
Okay.
thing. Okay, now try making it come back. There you go. Now, if that's true, if the angle makes that difference, you should be able to find an angle in which the spool doesn't move at all.
Okay.
Try it once.
Okay. So it should be about right in between.
Right in between those two, right?
Okay.
It's not going forward and not going backward.
Yeah.
Can you make it roll just a little bit?
I'll try.
Yeah.
Just a little higher.
A little higher, now a little lower.
Okay.
Okay, you get the general idea. So that's kind of a neat trick. It's really not a
Yeah.
magic spool, is it? You may have been to many parks, but you probably haven't been to a park like this one. It's all underwater. At the John Pennekamp Coral Reef State Park, just south of Miami, Florida, scientists and amateur and professional divers can explore at the bottom of the sea. They use all sorts of equipment, including mini submarines. These formations are formed by tiny animals that take calcium carbonate from the seawater to build their hard skeletons called coral. There are 47 different varieties of coral in the park. It's also the home of many other species of warm water animals and plants. Lobster bait attracts a black angelfish. Once they've sampled the bait, they may stay with the diver for hours, waiting for another handout. Sometimes huge schools of migrating fish, like these Bermuda chubs, pass through the park. A visitor has to be on the lookout for potentially dangerous animals, too. The sand shark is one of many shark species that live in these tropical waters. The diver handles this hawk-billed turtle carefully because, with its powerful jaws, it could bite off a finger. Nearby are oak beams from 16th and 17th century Spanish ships that either ran aground on the coral reefs or were plundered and sunk by the many pirates who roamed these waters hundreds of years ago. The plant and animal life, as well as the archaeological specimens, cannot be removed from the park without special permission. Many parks have been established to preserve a part of the natural world. None are more unusual than this special area on the bottom of the ocean, a coral reef that's been set aside as an underwater park. Have you ever seen one of those radiometers, Nicola?
No, I've never seen one before.
Well, they're sold in novelty shops and magic shops like
yeah.
that, and they put them in the window, and the sunlight falls on them, and they go around. So a lot of people think that it has to do with the light falling on it.
Yeah,
and it is
around.
true, but there's a little more to it than that. But my challenge for you is I want you to make the vanes go backwards.
Backwards. Okay, I'll try.
They're now going clockwise, right?
Yes, they
like
are.
the hands of a clock.
Yeah.
So I want you to eventually make them go counterclockwise.
Okay.
Let's take them over here where we have a little bit of control of the situation and see if I can explain why these little vanes are going around. First place, most of the air has been taken out of this little envelope. In fact, you can see there's a, you take the bottom off, you can see there's a stem there where
Yeah.
they took the air out.
Yeah.
Okay. There's still some air molecules left in there. I'll turn on this light.
Now it goes round.
Now
and
it goes around. It's going around
Fast.
faster, yes. Now think about this. One side of the vane are black, and
Yeah.
the other side are white, or silver colored. If there's still some air molecules in there, what's going to happen when the light falls on the dark side as compared to the light side as far as absorption is concerned?
Well, if the black absorbs the light, well, will the molecules start getting crazy?
Well, as a matter of fact, if what you said the black absorbs, what,
The
does
heat.
black absorb more than white?
Yes, it does. White. I think white reflects it, doesn't it? Yeah.
And black absorbs it. That's one of the reasons it's black, because it's absorbing all the wavelengths.
Yeah.
Okay, but now if the light then goes in and hits on the black side and that gets a little hotter, then the air molecules next to the black side are heated up, and that makes them move faster. So they bang onto the black side, and that gives it a push, and that's
Oh,
what
I
makes it
see.
go around like
Okay.
that. Okay. Well, if we're just heating up those vanes, then we should be able to do it without light if we just use heat.
Yeah, I think so.
Okay, here's a heating element.
Little heater.
Turn on my switch. That's what happens when you have light on it. Now we'll get rid of the light. And can you take the little thing and tip it sideways and stop the vanes from going around? Come.
Okay.
Okay.
There. Oops.
Well, they'll go around a little bit because we have some light in the room. But now, hold your hand over here. Tell me when it gets nice and hot.
It's already nice and hot.
Okay, now watch the vanes.
Going faster and faster.
We haven't increased the light at all, have we?
No. I think it's the heat then.
Yeah, it's definitely the heat, because if my theory is correct that we're heating up the black side even more now because we're direct heat, and it's invisible, going right through the glass and affecting the black side. But my challenge was make them go backwards.
Backwards, yeah. I
All
can't
right.
think of a way.
I'll give you a little help. Over there on the stove, I have a pot of hot water. So would you bring it over to the sink, and I'll get a pitcher of cold water.
Okay. Yep. There.
Okay, now I can set that there on my little beaker so it's nice and high. And you bring the hot water over here and pour it on there first. Now, what should happen, though?
Will it start going round and round again?
Same as the heating element.
Yeah.
Okay.
Here goes.
Sure
That's good.
enough.
Yeah, there it
Still
goes.
going counterclockwise, or clockwise, but faster.
Yes.
Okay, now,
Okay.
if it's true that heat makes it go clockwise, what if we took the heat away? In other words, we poured cold on it, like ice cube water.
Will it go backwards?
Well, now think about it. Think about the theory. What should happen?
Well, the black will. Let's see. All the heat will get off the black,
Yes, it'll give off the heat faster.
Yeah.
Okay.
and then the molecules, I guess, will go onto the white.
Well, the molecules
Well,
next to the white will be heated more.
Yeah, and then
Okay.
they'll go up and down again.
And they'll bang against the backside, so that should make them go counterclockwise.
Okay.
Okay?
So then,
Try it.
that's gonna work. Okay.
Going clockwise.
That's stopping.
Yeah, slowing down, stopping,
Now it's going the other way.
and finally going backwards.
There.
So we've sort of proved our theory.
We did it.
Yes.